by the way, welcome. If I haven't said welcome yet, welcome to the to the interview. Is Python your preferred language?
Yeah.
Okay, cool. All right. So for this problem, what we're gonna do is it's a problem called maximum path sum in a binary tree. All right. So your
Yeah.
input is gonna be a binary tree, and I can just go ahead and copy the definition for you here. So your input's gonna be a binary tree, and all the nodes are gonna have values, um, and then you need to return the sum of the nodes in the path that produce the largest sum. Right. So there's a path in the tree. There's many paths in the tree potentially, and each one has a sum, and you need to tell me the largest sum.
With the largest sum. So I'm guessing like there's probably negative values in there, right? Otherwise we would just sum everything.
Yes, there is a negative. And you wouldn't necessarily sum everything. Depends on how we want to do a path. But yes, there are negatives, which is why you can't sum everything.
Oh, right, right. Yeah. There's negatives. Working with the binary tree. So I mean, you can't sum everything
Well,
because
it
when you go,
depends on the shape of the tree, right?
yeah,
For now, I mean, let's say that for now, let's say that you can't like double back.
yeah, okay. So does it have to be like root to like a leaf node, or can can
Doesn't
can
have
it
to
be
be
like from left to right? Does that question make sense?
left to right. I don't know what that means.
So let's say you have a tree with three nodes. You have a left node, a root node, and a right node.
Okay. Okay.
And
Yeah.
you go from left node to right node for your path, or does it have to be root to left, root to right?
No, it can be left to the root.
It can be left to root. Okay.
Correct.
Okay, sounds good. Um, so I guess for a path from any given node, you can go up, left, or right. Um, yeah. Okay, I see.
I'm thinking actually
So,
as to maybe start us off. Let's
mhm.
say we can only go from parent to child. Let's not be able to go from left to root. So let's only do parent to
Okay.
child.
So if you're doing only parent to child, um, as a brute force option,
Okay.
we could just try every possible path.
Okay.
How many paths would that be? I think you have at each node you have two options, either go left or right. In the worst case, sometimes it might be like no, but in general there should be due to the n pa different paths that you can take. Uh, so let's see, what would be so the brute force option would take two to the n steps, and if we work with like an example maybe. So I wish there was an easier way to draw a tree on this, but
You can use a drawing tab.
a drawing tab.
Yeah, on the left.
Oh, I never saw this. Never seen this before. You're able to see what I draw?
Yes.
Okay. Okay. Cool. My bad. Okay. So let's consider like a tree. Right. First path, you have a path such as this, or maybe you stop at a path. Uh, hmm. Okay, let's see. So what are the options that you have? So it'd be more than 2 to the n possible solutions because you don't have to go all the way down to the leaf node. So then you also have the other option of just stopping at the spot. So either go left, go right, or stop at current node. And then what this could look like is basically I'm trying to see if there's any like repeated work here. Um,
Okay.
but I don't think you're. Oh, yeah. So I think what we can do is run some type of DFS or BFS. And we could run that algorithm in event time and just track the current sum that we have. And I believe we should be no, that's not true. Um, so if he did BFS, for example, it wouldn't consider if he went with the solution that I just said, it wouldn't consider the paths that start at like a subtree. For example, it wouldn't consider 2 then 4, right? It would consider 1, 2, and 4.
Yes.
But 2 and 4 could be the value that we want, right? For example, maybe our root node is -3, for example, here. Then the return value is 3. Um, so in that case, what we can try is,
Wait, sorry, why is this value 3? Oh, because you're counting the root. I see, okay.
yeah,
But the correct answer here should be 6, right?
like we would return 6 if we're picking between the two, yes.
Yes, okay, yeah, making sure. Okay.
Yeah. So now what does this mean? So one possible solution could be that starting at each node, what is the maximum sum that way? So then at the current node, um, you're considering current node plus left, current node plus right, and then left or right. Uh, and then we would do this for every node.
So at the current, you consider the current node plus left, current node plus right, and then not the current node, so just left or right. Okay, I see what you mean. Okay.
Yes. I'm trying to think what would be the runtime here. Uh, so I think you're still only visiting each node once, right? And these are all of one operations. So if you did this type of recursive DFS solution, um, they should still run in O of n time.
Yeah, if you check every node once, then yes. First for
Yeah,
time, yeah.
so we would have a DFS algorithm starting at the node, and then we'd visit left, visit right, um, and then for this specific node, we return you'd return max this. We do this for every node, and then we could have like a global variable that has like a max so far value. And then we can return that once our DFS is done running. Since we're only going left or right, we're not going back up to the parent. I We shouldn't be visiting a node multiple times with this algorithm. And yeah, so how does that look to you? This
That looks pretty
algorithm
good.
should run in oven time, oven space.
Yeah, that looks pretty good. Why do you need a global variable?
Um, Good question. Right, because we are returning the maximum value we've seen so far. And for when we visit left or visit right, you will also get the maximum value that comes out of the right tree or the left tree. So we actually shouldn't need this variable at all. The
Okay,
value that we get back should be the max.
okay, that looks about right.
Yep.
Why don't you go ahead and implement that? Yeah.
Cool. Yeah. So it's been a while since I've worked with trees. Cool. Uh, yeah, I think this should be okay. I wonder if it's possible for current value to be. No, these numbers would never be negative, I'm pretty sure.
For which?
So for example, as when we get our left return value or our right return value, this will
Yes.
always be bigger than 0 because of our base case.
You tell me.
Uh, Um, hmm. Maybe I should work with an example. Let's see. Hmm. Well, when we have, when we get to a root node, we return 0. So then left will return 0 when leaf is null. And then in this max calculation, we're comparing all the values. And in this case, left would be 0. So then when we go through this return process, it should never return a value less than 0.
Okay. Yeah, I agree.
Yeah. Okay. So here is, say, the solution
Okay.
so far. Yeah,
Well, I mean, now you know the follow up is that now you can go upwards.
right. So now what changes? Let's see. So, uh, so now with this follow up, we can have paths like this. You can have something like
Yeah.
this, whereas previously we couldn't. Uh, so what if we work our way up? Um, so now in this case, what we're doing is we're taking the left and we're adding it with the right. Right side could be a negative value. And if right side is a negative value, then you wouldn't add the right side. Same goes for the left side. Um, okay, so if we consider this for example, we have the left, the right, and then the current node. Uh, and in this case, our like the answer would be left plus right. And then we do the same thing over here on the right side, left plus right. And then this gets moved upwards towards this two node. And then you have the left side and the right side to work with. Uh, okay. So what are like the decisions we'd be making in this algorithm? So you could have just left, just right, left plus right. Um, if you're including left plus right, then you would also have to include the root node. Mm. Now, if you have a -2, for example, we're going back all the way up to the root. You can't just skip -2 to get to like the rest of the values in the left subtree. Um, so that means you have to take it. So what this means is first off, you'd probably need like a global variable representing like the maximum number we've seen so far. Because uh, this subtree right here, the 6, 4, and 7 subtree, this could be the maximum value. But when we propagate all the way up to 1, this -2 value would uh this -2 value would decrement this subtree's result. When we also propagate all the way back up, we have to go like this or like that. And does that make sense?
That makes
Uh,
sense. I
you
still
can't get
don't.
this entire tree.
Right. I mean, based on what you're saying here, I mean, this makes sense. But the part that I'm still not quite sure about is why do you need a global variable for this? You might need one, but I didn't understand that from your reason.
Um, let's copy. See. So I'm thinking about like when we return the value from here, right? The maximum value and from this subtree, like if we only considered this subtree for our like question, right? The answer here is 4 minus 2 plus 5, which is 7. But this route isn't accessible to 1. So it doesn't make sense to include this tree in like the return value.
Yep.
I'm thinking this should be like a global value that tracks the maximum that we've seen so far. But then when we when we return from this subtree, what we would want is the maximum that comes out of this left subtree, which would be this path. You go -2, then 5.
Mm-hmm.
So then the return value should be 3. Does that make sense?
Yeah, that makes sense.
Yeah. So that means we'd have to do two separate calculations. The maximum value from this left subtree, and then the return value that you provide from the DFS function. So I'm thinking we could um, you'd have this function, right? But we'd also have an inner DFS function, and then we'd also have like the results stored outside. Mm. So now, as we said, you can consider the left or the right. Yeah. So we have the left side and the right side. Um, and then there's three values to consider for the current node. There's the left side, the right side, there's left plus the current, so there would be 5 actually. And then there's left plus right plus current node. And then when we return a value, um, we return the maximum of left plus current and right plus current. So then we take all of these value, all of these variables, we also have let the result. Result then becomes the max of these 6 values. Then we return the max within these 2 values um, for
This
the
is
parent
your
tree.
global variable.
Yeah.
Okay.
So does that make sense? Um,
Yeah, I'm trying to set this is
so
your
at the
left tree, which is ignoring the node, right tree ignoring the current node. Left curl, which is if your cur is positive, this occurs positive. This is taking the entire subtree.
including,
Yes,
yeah,
That makes sense. I'm trying to think if you have overlapping cases because just these, or rather these cases specifically, are eligible for like being returned, but that's not an issue. I don't think if it's also put into the max. So I think that's okay. Go ahead.
Yeah. Okay. Cool. Yeah. So if this looks okay, I can implement it. I think the code will be very similar. So yeah, I wonder if I can just call this function. Cool. One thing I'm not too certain about. Not sure if I need to use some type of keyword here. If this was a class, I'm pretty sure you'd have to be like self dot result.
Yeah,
But
only if it's a
otherwise, yeah,
class. Yeah.
this is my solution.
Okay. Time and space.
Time and space should be the same. We're visiting each node once, and
Okay.
then yeah, space is also O of n. In the worst case, you have n stacks of recursion.
Yeah. What's the average space usage?
Average space usage. And I am actually not sure how we can calculate that. I'm just thinking. So at an average case,
That's okay.
I wonder.
You can think about that later.
Yeah,
It's
I'm
not a big
just
deal.
yeah.
All right. I want to move on to a
I
second
have no
problem.
idea.
To a
Yeah.
second problem, just to kind of move us along here. Okay, so this problem, I'll just continue below this.
Okay.
So this problem is called Alien Dictionary. Okay,
Okay.
and how it works is basically we're trying to decipher the alphabetical order of a different language. Okay,
Right.
so what your input is you have an input that is a list of string. Okay, and the information you're given is that this list is ordered. All the strings are sorted lexicographically. Do you know what that means?
Like ABC, but in this case, the aliens language.
Yeah, so let me give you an example. So this is an input, and
Right.
I'm telling you that this is sorted lexicographically. Okay?
Okay. Yeah.
And what that means is, for example, if you were, I mean, this is obviously not English; it's a different language, right? So, this is so for example, if you were to compare WRT and WRF, WRT is before WRF in the alphabetical order.
Yeah.
Does that make sense?
Yeah.
Okay. And then your return value is you need to return um, a string which consists of every letter that you have seen in a valid lexicographical order. Right? So for example,
Yeah.
in this case, you need to have a string which contains WRTF E. Yeah. I mean, so this is, I should put it this way. Oops. So this is a set of letters that you need to order in some way, and I'll just tell you for example,
Okay.
this one the answer is this. This is a valid answer.
Yeah.
So
Cool.
and there might be multiple answers, right? There might not be enough information in your list to give you the exact ordering, but you're always able to deduce relative ordering.
Right.
Okay, so this is your prompt. Please have a look. Let me know what you think. And just and I'll also just give you a second example. This is easier, obviously. Um, this should be
Yeah. Okay. Cool. So looking at this, right? Um, I'm just trying to think of how like I'm solving it, just with my eyeballs, right? As a human, right? So when I'm solving this, I'm comparing the first letter, and we can see that E, for example, comes after W, and we can also see that E comes after, or we can see R comes after E. And then if we keep doing the same thing, see the value R, see R, and then we see that T comes after R, and then comes after T. And now, if we go through this entire process, I'm pretty sure we're getting a directed graph here. Uh, so then is it fair to say
wait.
that,
Hold on. I want to just when you say so the syntax, I'm a bit unsure. What do you mean by arrow?
so F comes after T?
Okay, I've come. So like this. So for example, like sort of like this, right? If we're to compare.
Yes.
Okay, that's fine. Just double checking. Okay.
Okay. So if we represent it like this, it's easy to see that we're forming a graph based off these words. Um, Now, could we have invalid? Could the sorted list of strings, could it contain like an in like a lexicographic order that's like not possible?
What do you mean by that? All strings
For
can be
example,
sorted in lexicographic order, so I'm a bit confused.
is it possible for like this lexicographical string to suggest that, hey, E comes after W, but then W also comes after E? I guess no, it wouldn't be. It wouldn't be. It's sorted. Okay, cool. So let's go through this entire graph. Then we have T. This suggests that F comes after T. No, it doesn't. So the issue with this thing that I'm doing here, that so you have WRT, WRF. Um, when you look at like the third letter of each word, it could suggest something like R comes after T, but that's not true. And that's only possible because it's the third letter of the word. Does that make like did what I just say make sense?
Yes. So R is less than T. Oh, sorry. So this you're saying T is less than R is the syntax,
Right,
right?
yeah.
I don't
But
think
that
that's
wouldn't be,
true. I think that's
yeah,
I don't think that's true. I think from this you can see that R is less than T.
yeah. What I'm saying is that with the way that I was going through like the problem over here, um, this could be suggested. So I'm saying like this is something we need to figure out how to avoid.
I don't think you can find a contradiction in that sense. Like for example, if you look at at this pair over here, you know that R must be less than T because ER comes before ETT,
Hmm.
right? Do you see evidence of otherwise in this list?
I don't.
Yeah.
Right, because it's again sorted. Sorry. Yeah. Okay, let's just keep going. Okay. Think about this. What if we compared each word? Maybe have WRT and we have WRF. And when we look at this, we can see that um, T comes before F, right? That's what decides why WRF is after WRT.
Yes, correct.
Yeah. And we can easily detect this by going through both of these words, and we'll see that, hey, the W's match, the R matches, and then the only thing that doesn't match is T and F. And then we could go through um, the entire list that way. Now we have cases where one word, like if we go through the array this way, we'll have cases such as ER and ETT. In this case, there's just a word that is bigger, right? Um, so now, in this case, we can see that R is bigger than T, or R comes before T. But I wonder what would happen in a case such as this, right? Where you have ER and then ERG. What does this mean? Is does this mean, yeah,
What does
so
this
would
mean?
this suggest that R is bigger than G, and that's why?
No. So this actually would not tell you any information. So in normal conditions for lexicographical ordering, if you have AN vs A and D, AN would still be considered less than A and D because it has fewer characters.
Okay, got it. So I guess in such a case, for example, we can get this type of information, but if you have something like this, we can just ignore the comparison. Okay. So now if we go through this list, what type of graph do we get? So WRT, the next is WRF and ER. This suggests that W comes before E. Then you have ER and ETT. Cool. Now I want to, now I'm wondering, like, is there a way to reconstruct a sorted character like string? Um, I wonder, so could the return value contain like two separate, two separate outputs? Like maybe you have something like A, B, C, and then D, E, F, but there's nothing suggesting that D ever comes after A or B or C. Does that question make sense?
Like if this is your input,
Right, yeah.
I mean, this is your input, then all you notice is that A is
Sorry, no,
before B.
sorry, not, this is not the input, but could you have a solution where your input array suggests that A comes out B, like C comes after B and B comes after A, and then you have the same setup but with D, E, and F. So in this case, there's nothing suggesting that D comes. There's nothing suggesting that D, E, F is after A, B, and C.
Yes, that's correct. So you have two valid answers. You have A, B, C, D, F, and D of A, B, C.
Okay, so that's how we want the return value.
Yes.
Cool. Um,
I mean, actually, now look at it. You
okay.
actually have almost. You actually have way more valid solutions. You could do like you could do, as long as you have A after A before D, you can have anything like this. Like
Okay.
this is your valid output, right? You can have anything there.
Yeah. Cool. How do I construct? So I'm trying to think about how I can construct a solution because now like we do have all of like the information extracted. We could
Okay.
represent this as like an adjacency list or something similar. If we did do that, what would that look like?
So I think so. Actually, like okay, so you can do that, but if you have your graph already, you already have all the information you need to produce the output,
Right.
right? Like every node of your graph is a character, and so you know it must show up in the output somewhere,
Yeah.
and you know it must show up in the output exactly once, right? In other words, you need
Right.
to traverse the graph some way once exactly,
Yeah.
and you need to traverse the graph in a way that all of these rules are obeyed.
See. Um. Okay. So think to start, like if we did, like hypothetically, if we did some type of DFS or BFS, the root would be T in this case because T is the first value that shows up. No,
Um,
no, it wouldn't. No, it wouldn't. It would be W. Right.
it would be.
Actually,
I'm trying to look at
not
this thing. I
true.
think that's right. It could be. I think there could be more than one answer. Let me just. I mean, it could be W. I think yeah. I think it might have to be W. Yeah. Yeah, it has to be W. Yes. I
It
think in
has
the
to be W.
yeah. I think in the example I gave you, there's only one correct answer. I mean, at this point, I'll just post it for you. I'll post it over here.
Right. So if we did a DFS starting at W, we would get this solution. I just don't know if this would work every time. Um,
You would also need
and
to
then,
know to start at W.
sorry?
You would also need to know that you need to start at W.
Yeah. And that might not also be always true either.
That's right. That might not always be the first letter.
So I'm thinking, what if we had like a doubly linked list maybe? Um, So my thought process is if you have a doubly linked list, which we can definitely construct if we had like an adjacency list. Um, if you have a doubly linked list, then you can traverse all the way to the head of the list, and then you can go through the linked list again, and then get this output that we're looking for. Um,
Sure.
I think so. In our first example, that should work, but I'm not sure how we would deal with this case right here. Are you able to see what I highlight?
Yes.
Okay.
Yeah, you see the issue with this is that like so you can
Um,
generate these two disjoint graphs, um,
yeah.
but then they are graphs, so you wouldn't necessarily be able to make a linked list, or at least not trivially. Like for example, you can imagine for ABC, like you can know ABC, you might also know that B is going into like Z or something, and then you would need to flatten this to a linked
Mhm.
list. It's doable. I'm not saying it's not doable. I'm just saying that there are other cases you would need to handle.
Yeah. Mm. Obviously, if you could DFS from A, then this would be a lot more trivial. It's just I'm not sure where to start, and I don't know how to figure that out either. When you see the first comparison, this doesn't suggest that we should start at T. So I guess my issue is how do I know where to start? Or maybe
Okay.
there's like a solution where I don't need to know this. Um,
So the algorithm that's being tested here after you construct a graph is called toposort, topological sorting of a graph.
topological sort.
Now,
Yeah.
that is the default solution, but you can do this with DFS. You would just need to handle more of the logic yourself. Like specifically, um, specifically what I mean is like toposort isn't magical. It still is just code. If you want to replicate
Mhm.
it yourself, for example, you would need to do you would need to generate shouldn't generate you need to track states you need to track the state along while you traverse more than just a regular DFS. But look at your case over here, right? So you're saying you're not sure what to do in, let's say, this case.
Mhm.
One way to check is, okay, you know what? Let's talk about two different cases. The first case is these disjoint sections, right? For if you just
Yeah.
look at the first on the island, right? I mean, you could have A B, A B C Z, or A B Z C, right?
Yeah.
Both are valid,
Yeah.
right? So we don't really care how we traverse in terms of like in this case BFS or DFS. I mean, let's just call it
Mhm.
DFS, right? As long as you can, as long as you can traverse the entire island, you're going to be okay. Now, BFS might be a bit easier, quote unquote, easier in the sense that you're going from A, you'll you'll go to all of the second layer ones like B, you know, and then you go to all
Yeah.
the third layer ones like C, Z, etc. So BFS would be more correct, but you can still do it DFS, right? So in this
Right.
case, the order doesn't really matter. Like you just have to do every island DFS or BFS, and then just append it with whatever answer comes afterwards.
Right.
And then for the above for the above one, like where everything is connected, how you determine where you start in general, and this also applies to the bottom one. How you determine where to start is you need to find the node that has no incoming edge.
Oh, that makes sense. Yeah.
So, you might have, let's call it, five nodes with no incoming edges. Then you know that they must be disjoint islands.
Yeah.
So that means you need to do it five times. So actually, these two cases are actually the same case basically, right? Every time you find a node that doesn't have an incoming edge, you know that it must be the starting point of its own island, and then
Yeah,
you just run your BFS on it, and then you do it for all the different islands, and you just append the answer together.
yeah, makes sense. I also need to study up on Taposor because I definitely forget how to implement it.
Yeah.
But yeah,
Okay.
yeah, that makes sense.
Yeah. Gotcha. Yeah. That's good. That's good. All right. Anyways, um, we'll end the interview here. We'll go to the
Yeah.
feedback. Go to some questions. I mean, this is a good place to to start about this question, right? How do you feel about this problem? Like, was it? Because I mean, you made some progress on the first part of the problem, which is the graph generation.
Yeah.
Like, you got that part mostly figured out. It did look like you slowed down a lot when it came to actually traversing the graph. Why do you think that was?
Um, I honestly think like I forgot like the graph properties. Um, like I need to brush up on like the graph algorithms, specifically like topological sort. Like that didn't come to mind as like a possible option.
Okay, yeah.
Um, this is
So
hindsight, but once you did mention that, hey, there is no like the starting node is not going to have any incoming edges. I feel like that's something I should just know.
yeah,
Like,
that's one
yeah,
of the properties.
yeah,
Okay. I mean, you just gotta study up on that. I mean, I'm sure you can figure it out later on if you do get it. It's just a matter of execution. Problems
yeah,
like this, when you get into Leetcode hard territory, it's not just a matter of like, do you have the right idea? It's that you also have to implement it. And not always, but oftentimes these problems require like two or more components to be implemented, right? Like the
yeah,
first component, for example, take this alien dictionary program, right? The first component is, can you generate the adjacency list or the edge list, right? Like, can you generate this data structure? And the second part is, okay, given a graph, can you perform topo sort, right? So in this case, this problem is actually quite well laid out in that it's just like it's a hard problem made out of two fairly easy medium problems, right? And so this
yeah,
kind of problem is just basically an execution problem, right? Like, can you figure that out that it is two medium problems, and then write it out and not make mistakes, right?
mhm,
So that's one aspect you definitely want to just brush up on in general. And this is a strategy that you should use, right? Just identifying how this problem decomposes. Very often, a hard problem will decompose.
yeah. Just smaller portions
That's right.
decompose into, yeah, yeah,
Um, and then regarding the first problem is interesting in that, I think that the first problem actually was interesting because the follow up question was actually the original question, like the original like hard problem. I think
yeah,
given that I asked the easier version first and then asked a hard one, he did quite well. Right, I gave you the easy problem first. That was like a medium level, and then I gave you a follow up, which was like another medium level problem. Right, now that problem also composes two different problems, but in a more like integrated manner. Like, it's not like two. It's not like A then B, right? It's like you do the problem the one way, and then you modify the first problem to do it a different way. So the learning there really
yeah,
is like, if you were to just be given the hard problem up front, right? In your own head, you have to try to break it down. Hey, what is the easier version of this problem, right? How can I solve that first? But yeah, I didn't
yeah.
ask you the hard problem, the hard version of that straight up, so we won't know how well you would have done there. But I think that was a fairly realistic problem, in that I think a lot of interviewers will ask it the way I have. So I think from that, I think you did pretty good. I don't have any concerns there.
Thank you. Yeah. So I guess two things to look at when I'm solving these types of problems is look at if the problem decomposes into smaller problems, or maybe consider like an easier version of the problem first.
Yes, I mean that's just generally good strategy. it's particularly important
Mhm.
as a strategy in hard problems because many hard problems are just two problems composed together. So that's why it's like extra important to be aware.
Yeah.
Okay, any
Well,
questions?
no, wouldn't say so.
Okay, well, in that case,
Yeah.
thanks for coming out. Take care.
Thank you as well.